Rotational dynamics and kinematics has an awful lot in common with what we've already seen in a straight line. For example, if we take a wheel of radius r and we put a spot on it at the bottom, if it rolls around one complete revolution and gets back to the bottom, we know that the distance covered will be the circumference, or 2 pi times r. If it rolls around so that it's up at the top, the distance will only be half of that, or pi times r. So in general, if we use a different kind of angular measure instead of degrees, if we use radians, and there are 2 pi radians in 360 degrees, then we could write a simple formula for the distance the wheel travels in terms of the angle that it turns through, and that would be x equals r theta. The only bad thing about radians is that if you're trying to keep track of units, radians don't really count. They could pop in or pop out, and there's nothing to really worry about there. On the left here for x we have meters, on the right we have meters and radians. So they don't match up exactly, but radians are the only unit that we don't have to worry about this for. The next step would be to look at velocity. So we could take the time derivative of this equation, x equals r theta. On the left, we get dx dt, which is just velocity. And on the right, we have to use the product rule to expand time derivative of r theta. We get r d theta dt plus theta dr dt. If the wheel's radius isn't changing, dr dt will be 0. And that's generally the case, not always, but if dr dt equals 0, we can write v equals r d theta dt. We introduce omega as an abbreviation for d theta dt. This is the angular velocity, and we're going to measure it in radians per second, although it's more common to see it in RPM, revolutions per minute. To convert, you would take radians per second, multiply by 60 seconds per minute to get rid of seconds and put minutes on the bottom, then multiply by 1 revolution over 2 pi radians to get rid of radians and put revolutions on the top. The next thing we would look at is acceleration, which is a time derivative of velocity. So dv dt is a, and then we take ddt of r omega. Again, we're going to get r d omega dt, and then omega dr dt, and we still assume that the radius of the wheel doesn't change. So we get a is r times d omega dt, or r times alpha, where alpha is the angular acceleration, and we measure that in radians per second squared. We could actually substitute these things into the old kinematic equations from a long time ago. For example, v final squared is v initial squared plus 2a delta x. We can put in v is r omega, v initial is r omega initial, a is r alpha, x final is r theta final, x initial is r theta initial. We realize we could cancel out the r's, and we get an equation like this. This looks exactly like our kinematic equation for regular velocity, for translational velocity, but now we've written it for these angular accelerations and velocities. And we could actually make a general replacement using this same procedure all through our 3 kinematic equations, where we replace x with theta, v with omega, and a with alpha. And that gives us these 3 equations for our kinematic equations of rotation. We can then answer a whole bunch of similar questions to what we saw in the very beginning when we looked at translational kinematics. Let's say, for example, we have a motor that starts at rest and gets to 3,600 RPMs in 0.28 seconds. We can ask, what is its angular acceleration? How many rotations does it make while it's getting up to speed? We put in what we know. Omega 0 is 0, t is 0.28 seconds. Omega we convert from 3,600 RPMs to 377 radians per second. We use omega final is alpha t plus omega initial, and we find alpha is 1,346 radians per second squared. To find the number of rotations it makes, we can use the long kinematic equation. We put in what we know. We might as well set theta I equal to 0, since there's no point in calling it anything other than 0. And when we do this, we get 52.77 radians for the total angular displacement. That's not really the answer. Since we want revolutions, we have to divide by 2 pi. It's really about 8.4 revolutions. We can do one more example. If we say we have a fan spinning at 40 radians per second, and then we suddenly cause an angular acceleration of -5 radians per second squared to slow it down, typical questions we could ask: how far will it turn until omega equals 0, or rather how long? And then when will it reach theta f of 50 if we assume theta I is 0 radians at t equals 0? So first we set omega initial at 40, omega final at 0, alpha is -5. We solve for t and see that it takes 8 seconds. Then theta final we know will be 50 in this question. We know the angular acceleration, we know the initial angular velocity, we set the initial angular position to 0, we solve for t. This gives us two solutions, and they're both positive, 1.367 seconds and 14.63 seconds. We get two solutions that are both positive. These are both valid for us, and the reason they are, we never said that alpha is going to change, that alpha will stop once omega stops. So what happens is the fan spins down, it very quickly turns through 50 radians as it's spinning down. When it comes to complete stop, then it reverses because the angular acceleration of -5 radians per second squared is still present. So it unwinds all the angle that it turned through, and when it's back to 50 radians for the second time, that's at 14.6 seconds. Just like the original kinematic equations, these are all for constant acceleration, only it's now angular acceleration. So you have to keep that in mind. These things are all vectors, just like all the translational kinematic variables are vectors. The way you find the direction is take the fingers of your right hand and curl them in the direction of rotation. Your thumb points in the vector's direction. We can then look at energy. Once we learned about conservation of energy, EI equals EF, the next thing we did was we tried to find every possible kind of energy we could and just make a list of them. For translational kinetic energy, we had 1/2 mv squared. We can guess that for rotational kinetic energy, V is going to become omega, but what happens to M? We know that M is a resistance to acceleration, so we need something that represents a resistance to angular acceleration to take the place of M. And this is called the moment of inertia. We're going to use I to represent it, and this is more than just the mass itself. The distribution matters. Kind of like center of mass, only this is yet another higher function of position than center of mass. If you imagine spinning a stick or a baton or a flashlight or something in your hand, if the density changes with position and the part right under your hand is very high density, it's still easy to spin it. If the part far from your hands, if that's where most of the mass is, that will be much harder to spin. The general formula for moment of inertia: we take the square of the distance between the rotational axis and the little tiny point mass dm that makes up this object, and we do that integral over all the masses. So we have to break something up into an infinite number of little pieces of mass, multiply each mass by the square of its distance to the rotational axis, and then add it all together. This is really a problem for our multivariable calculus because in reality, moment of inertia is a tensor, not a vector or a scalar. We're going to ignore that and treat it just like a scalar in this class. That'll be good enough for us, and you won't have to do these integrals. You can look them up in the book or on Google. Our rotational kinetic energy formula is then 1/2 I omega squared. If we look up rotational, or the moment of inertia for a solid sphere, we get 2/5 mass times the radius of the sphere squared. A shell, on the other hand, we would have I equals 2/3 mr squared. The reason for this, if we look at the shell, all of the mass, except for this part near the axis, is very far from the rotational axis. For the sphere, the solid sphere, there's mass all around this axis and out here and out here. It's not just out at the edges. So for the same mass and the same radius, a solid sphere would be easier to rotate than a spherical shell. If we treat the bowling ball as a solid sphere, and we say it has a radius of 0.1053 meters and a mass of 7 kilograms, and it's rotating at 85 radians per second, we can find its kinetic energy rotation very easily just by plugging these things in. and we get about 112 joules. You can find these tables of moments of inertia. Another one you'll find is moment of inertia of a point mass. That is given as mr squared. The r can't be the size of the point mass because the point mass has 0 size. What this r means here is the distance from the point mass to the rotational axis. There's something connected with this called the parallel axis theorem that we can make use of. This says if we know this moment of inertia through one axis, we can find it through a parallel axis a distance x away by this. New moment of inertia is old one plus mx squared. If we imagine we're spinning a yardstick or a baton or something about the center, sort of the way you would twirl it naturally, the moment of inertia, we do the calculus and get ml squared over 12. If you want to spin it around its end instead, which is significantly harder, the parallel axis theorem says we have to take this ml squared over 12, and then we add to it m times this distance squared. The distance is L over 2. It's half the length of the stick. We can put those together, we get a common denominator, and we find that it's ml squared over 3. And you can look that up in tables of moments of inertia, and you'll see it's correct. A sphere rotating through its center, we get 2/5 mr squared. What if we're trying to rotate it? We've glued the side of it to a stick, and we're trying to spin the whole thing around. Through this axis, we'd get 2/5 mr squared plus mx squared, but now this distance we've moved, x, is also r. So 2/5 mr squared plus mr squared is 7/5 mr squared. What if we decided to tie the same sphere to a very long string, where L, which is the distance from the edge to the rotational axis, is much, much larger than r? Then we get the original value for the sphere plus m times x squared, where x is r plus L. So we get something like this if we wanted to be exactly correct. However, if L is very, very large compared to r, we'd be approximating it like this. I is ml squared. If instead we call the length of the string r, we see where we get the point mass formula.